We are now going to look at acid catalyzed ring opening of an epoxide. This, I'm going to use the exact same epoxide I used for nucleophilic ring opening because I want you to see what's different in terms of stereoselectivity and regioselectivity. There's actually no stereoselectivity difference, but there is regiochemistry difference. And so I want to make sure that I show that to you. So again, I like to draw my epoxides out with wedges and dashes. And you could have a variety of different groups coming off. And it may or may not be chiral based on what's on these positions. So again, my carbon on my right is chiral. The one on my left is not. Now this ring opening is still going to result in the formation of alcohols. But what's on the arrow is very different. You will need to note whether what's on the arrow is a nucleophile or whether it's an acid. They're very different. Nucleophiles are bases. They've got negative charges. They are electron pair donors. They add to the less substituted carbon. If, on the other hand, you do this ring opening in an acid, you're going to protonate first. And that's extremely important because that means that this ring will have carbocation-like character. It's not going to form a carbocation, but you're going to think about it like it is one. And that means that your incoming nucleophile, because it will be added after the protonation, will attack the more sterically hindered side. So you will have different major and minor products from what we had before, even though we still form the same products. So, in these types of reactions, you use a dilute acid. Now, if you want the solvent to add as the nucleophile, which is most often the case, you need to use a dilute oxyacid. If, on the other hand, you want the halogen to add in the second step, you use a hydrogen halide. Typically, though, you want to avoid those types of acids. So the acid you would use, again, is some dilute oxyacid. Sulfuric acid's our favorite, but you can use others. And then add a solvent. In the book they show water, so I'm going to use an alcohol to make this just slightly different. I'm going to keep it simple though. I'm going to use methanol. Now, as you look at what's available to you, the strongest acid or base is what you want to pay attention to. Now, in this case you don't have a base, you have an acid. You have sulfuric acid. Acids are proton donors. You're going to donate a proton. That's what acids do. Now there are actually a couple of choices for where that proton goes. It could go to the solvent, and that happens. There's no reason why it can't go to the methanol. It just doesn't do anything productive. But you could also give the proton to the oxygen of the epoxide, and that is going to do something productive for you, so that's what we're going to show. The oxygen acts as the electron pair donor, picks up the proton, and the sulfuric acid gives up the proton. And this is what we do first. This is the big difference in what happens and when it happens. If you go back to the nucleophilic opening of an epoxide, you add the nucleophile first, then you protonate. Here we are protonating first, then doing the nucleophile. So the order of operations is critical as to what happens and why. This is an order of operations problem. So what we get as an intermediate in this particular case is something like an alkyl oxonium ion. There is positive charge delocalized through this three-membered ring. And so this positive charge is not completely localized on that oxygen. It is delocalized onto the two carbons of this ring by induction. And they do bear some of this partial positive charge. It does not form a carbocation. But you need to think about it like a carbocation because this positive charge is delocalized through these three atoms of the ring. Now the carbon there on the left is a tertiary carbon, and the carbon on the right is a secondary carbon. And when you think about who can handle positive charge better, it's a tertiary carbon. And so that tertiary carbon is a better electron pair donor by induction. Okay, so it's going to be donating more electron density toward that oxygen. That oxygen really needs it at this moment in time. Now, you need to take care of that positive charge. One way is, of course, to lose the proton. The other options are to lose a bond to one of these two carbons. And they don't want to just give up a bond. They need to have somebody add in order for that to occur. So this is where your nucleophile comes in, depending on what your nucleophile is. In our case, it's our solvent, and that will often be the case. You need to find the atom that is the electron pair donor. Now, if you'd used a hydrogen halide, it would likely be the halide that is the nucleophile at this point, unless you were doing this in a dilute solution. Then it may or may not be. But then you've got confusion, so don't do that. Typically, though, it is your solvent. So again, there are two choices for this oxygen. It's our mole attacking our tent with a flag. So we want to knock down the tent. He's going to burrow underneath and do this SN2 substitution. It is most likely to add to the tertiary carbon. Now, as that happens, you can't have 5 bonds to carbon, so a bond is going to break. And this will be the carbon-oxygen bond for 2 reasons. Number 1, you relieve the angle strain of the 3-membered ring, and number 2, that bond is already polarized toward oxygen, since oxygen's got a positive charge, and oxygen is more electronegative. This is what is going to happen most of the time. Sometimes, though, this nucleophile could add to this secondary carbon, and you could break the other carbon-oxygen bond in the ring. Both of these things can happen. So, show both. So for our major product, we had our nucleophile adding to this tertiary carbon. And again, I don't know what your groups are, but what is a wedge? Stays a wedge. And what is a dash? Stays a dash. What is a wedge? Stays a wedge. And what is a dash? Stays a dash. Minor product also forms. What is a wedge? Stays a wedge. What is a dash? Stays a dash. What is a wedge? Stays a wedge. And what is a dash? Stays a dash. Now all you need to do is remove the proton from the OCH3 oxygen. And this can be done with another solvent molecule. And you can show this from the major and the minor product. Doesn't matter which one. Mechanistically, we would normally show this from the major. I'll show it from both. You just remove the proton, give electrons back. Remove the proton, give electrons back. It doesn't matter which one you want to show it from, but typically you just show it from one. No. At the end of the day, what do you have?
2 minutes.
Well,
Let's record.
you've made your alcohol from the epoxide.
Have to run as soon as I can get out of here. That was a little longer than I expected.
So that OH group up there, that's the oxygen from the initial epoxide.
You've been loving your sleeping as much as I let you love it. Are you drawings that appear on the screen. Takes apparently forever to draw.
and those will be the products you form. So again, the incoming nucleophile part on both of these is added second. Okay, that's the important thing to remember. And the proton that is added first. Order of operations is the key to knowing what to do and when to do it. If you protonate the epoxide first, add your nucleophile to the more substituted carbon preferentially. If you add the nucleophile first, add your nucleophile to the less substituted carbon preferentially. Either way, these are the two products you would form. It's just a matter of who's major and who's minor. So be aware of order of operations, and that's all about paying attention to what's going on.